of education that are still with us today, but really it stretches all the way back to the Romans, who systematically stamped out this ancient knowledge, and there's evidence that they did that. Because it was the Romans that stamped it out, the places people end up looking for the ancient wisdom is in places that the Romans didn't get to, like India and Tibet and China and even Central America or New Zealand. So I would argue that makes understanding the precession of the equinoxes pretty relevant. And it is because it is the key to seeing the evidence for points 1, 2, and 3. And the good news is it's not really that difficult to understand precession. To explain precession, I like to use this analogy I call the analogy of the dining room. Let's pretend you're in your dining room. You've got a round table, and you've got 4 walls. Now this dining room with the round table represents Earth's orbit around the Sun. We'll put the Sun in the center of the table. And the table, the edge of the table, represents Earth's orbit. So let's add the Earth. And it orbits in this direction. In this dining room, north is up. Okay, we'll be north hemisphere centric here. Now this part is important. If you're on the Earth during the daytime, of course, you're facing the Sun. When Earth turns around, you're looking out into the night. Stars are in all directions, but they're on all the walls. They're on the ceiling and the floor. If you're in the northern hemisphere, you can't see the floor, but at nighttime you'll be able to see the stars on the ceiling, and you'll be able to see the stars on some of the walls. But let's note that the wall that's across from you at any given time, you won't be able to see those stars, because when you turn that way, when you're on the side of the Earth that's turned towards the Sun, you're not seeing any stars because the Sun comes up and it blocks them all out. So let's see it again. Let's move the Earth forward here on its orbit. Here we are. We've moved to a new season. New stars are becoming visible, new walls. Remember, when it's day for us, it's because we're facing the Sun, so we can't see the stars on that wall across there. But when the Earth turns, nighttime, we can see the stars on that wall over there. So, importantly, when we're in the same position on the table, the same stars and constellations should be in the same place. When we get around to this point on the table, we look on, oh, look, there's the stars on that wall coming into place. You know, we got the constellation of the paddle up there on that wall back there. But if we're at the exact same day each year, the exact same time, we should see the same stars. If we're facing out from, and we're on the same point on the table, and the Earth has turned the same amount, we should see the same stars in the same angle in the sky. Well, of course we know that the calendar slips a little bit, so how do we know when we're exactly in the same point on our orbit around the table any given day of the year? Remember that the Earth turns on its, each day it rotates around. That's one day, but it doesn't do it in an even number to get back to the exact same point on the table. So that's why we have a little bit of slippage in the calendar, and we use the leap years to bring it back into place. But that's why these points on the orbit, known as the solstices and the equinoxes, are such handy references. They're so helpful. Because when we get to the solstice, those are determined by our position in relationship to the Sun. And when we get to the solstice, when we get to the equinox, we're back at, if we can accurately figure out that we're at a solstice or an equinox, we know we're back at the same point on the table. So the calendar may slip around, but we're going to bring it back in line using the leap years, and that's why we'll bring the calendar back in line with it where we actually are. But the equinoxes and the solstices, those are like handles that we can grasp in the darkness, and they divide the year, the orbit, into quarters. We've got the March equinox, the June solstice, then we get around to another equinox, the September equinox, and then the December solstice, and then we're back around to the March equinox again. In the northern hemisphere, we call that the spring equinox in March, the summer solstice in June, the fall equinox in September and the winter solstice in December. Now let's move the Earth over here to the spring equinox, which is a very important point. It's the start of the year in many ancient calendars. Now the same stars should be seen at the same time, just as we said before. Let's say the same time, for instance, just before sunrise on the spring equinox, we should see the same stars in the same places. However, something happens that we don't expect, a surprise. The same stars are not in precisely the same spot at precisely the same point in the orbit each year. When we get around to the exact point on the table where we were before, and it's coming around to sunrise on spring equinox, there's actually a tiny bit of slippage. Now it's very, very subtle, but actually the constellations that are there in the sky right above where the sun's going to come up, right before the sunrise on the spring equinox, they slowly shift, very slowly. Why? Well, it's because of a phenomenon called precession. It's caused by the physics principle of the conservation of angular momentum, but it's a slow wobble, like a gyroscope wobble. The axis of the Earth actually traces out a circle, just like a gyroscope will sometimes do as it goes around. Actually, both the North and the South Pole, if you had an imaginary pole sticking out, both of those would be tracing out this gyroscopic circle. It's a wobble in the Earth. And if you think about it, you'll perceive that wobble over time will actually change the angle that we're looking at the stars, even if we come back to the exact same point on the table. And that is precession. So let's examine what that looks like for an observer on the ground. Now here's a drawing depicting the eastern horizon. We're looking at the constellations that are in the sky before the sunrise on the spring equinox. Now this is depicting a situation thousands of years ago. It's actually a time period called the Age of Gemini. Now I've drawn in the constellations in blue. Those are the actual constellations that would have been in this position where the sun is getting ready to rise. And I've created a horizon there. That's that black arc. That arc represents the horizon. So below that you can't see those stars. The Earth, of course, is still rotating, so eventually, as it rotates, towards the east, those constellations will pop above the horizon, but something else is going to pop above the horizon first, and that's going to be the sun, so you won't see those constellations. But those constellations that are above the horizon, before the sun comes up, as the sky is getting lighter and lighter, you'll still see them in the east. The west will still be a little bit darker, but the east will start lightening up. But those constellations that are there where the sun's going to come up, those are very important. The sun's going to come up in the constellation of Gemini there. And before it comes up, you'll be able to see the stars of Gemini above the horizon as it starts to get lighter. You'll also see the stars of Orion above the horizon. And according to our dining room table analogy, those stars should be the same stars when we get to that exact same point, the spring equinox, before the sun comes up every year on that exact same day. But precession is going to cause a slippage. It's going to actually delay those stars to where they're not there at their exact appointed time. When we get around to the spring equinox and the sun is getting ready to come up, those stars will actually, over time, will be delayed, and that's because of that circle that the North Pole is tracing out in that precessional gyroscopic wobble of the Earth. And Orion will actually be delayed. And you can see in this diagram, after thousands of years, here we are on the dawn of the spring equinox, but we've got a very different situation. There's that black line that represents the horizon. Now Orion, he used to be much higher in the sky, but he's been delayed. Gemini is no longer the zodiac constellation that the sun is going to rise in on the morning of the spring equinox, and now there's a new constellation in their place on the morning of the spring equinox Taurus is now above the horizon, and the sun is going to rise in Taurus, and Orion will now still be below the horizon on the morning of the spring equinox. And so we've moved to a different age. This is a precessional age, has shifted from Gemini to Taurus. Now, if you watch this closely, if you're an amateur astronomer and you go out each night, you're going to be able to notice this phenomenon or precession. Well, it's very, very slow. And remember, this isn't a nightly thing. The stars do shift each night because we're going around the table, so we're seeing a slightly different patch of wall each night. We're talking about on the exact same day each year, this shift is going to take place. How long will you have to look before you see 1 degree of change on the, for instance, the morning of the spring equinox? Before you're able to measure 1 degree of change from one spring equinox to the next, you have to actually go through 71.6 years. You're not even going to see 1 degree from one equinox to the next. You're going to see 1 degree every 71.6 years of slippage. Orion will be 1 degree behind where he was after 71.6 years. He'll be 1 degree lower in the sky on the spring equinox. So if you start at the age of 20, you can keep good records until you're 91.6 years old. You might perceive that 1 degree of difference. So it's a very slow process, but 71.6 years, 1 degree. For ease of memory and encoding, we can round that up to 72. And if you want to get 3 degrees, you have to multiply it by 3, you get 216. If you want to get 30 degrees, you have to multiply it by 30, you get 2,160 years. And since the zodiac divides the sky up into 12 signs, 360-degree circle, 30 degrees each, it takes 2,160 years approximately to move from one sign to the next. On the spring equinox, the constellation that the sun is rising in, we just showed it going from Gemini to Taurus, the age of Gemini giving way to the age of Taurus. After another 2,160 years, age of Aries. Then another 2,160 years, age of Pisces. And we're getting towards the end of that one right now. What do you think the next age is going to be, the new age that will dawn? And you guessed it, that's the age of Aquarius. We're getting towards that transition right now. But that's where the precessional numbers come from. We've already talked about the 72, the 2,160. That gives us, you can add zeros, take away zeros when you're encoding them in mythology. So you could say 216, important precessional number. If you divide that in half, you get 108, extremely important precessional number. If you double 216, you get 432. All these are found in ancient mythology, and they show a very precise understanding of precession long before conventional history. Conventional history thinks that Hipparchus, who lived from 190 to 120 BC approximately, 190 BC to 120, was the first one to understand precession. And then after him, following on his work, Ptolemy from AD 90 to AD 168, he definitely wrote about it. But they didn't even know 1 degree every 72 years. They approximated 1 degree every 100 years. So now that's what conventional history says, but if you look in the ancient mythology, and there's other people who have pointed this out before me, they show that the legends or the myths, for instance, we know that the ancient Egyptians associated Orion, the constellation, with the god Osiris. Well, he was murdered by his brother Set, along with 72 henchmen. Set and his 72 henchmen killed Osiris and threw him in the water. Well, look at that's encoding what's happening in the celestial phenomena. Osiris is being held down, slowly. He's being held down, delayed, held down beneath the horizon, and a new constellation is usurping his rightful place. And that constellation, Set, there's some evidence, was associated with Taurus. You can see the angular shape of the constellation Taurus. Look at the angular shape of the ears of the Set beast, the head of Set. Also, there's some other features about Set, but Taurus usurps Osiris's place and the son of Osiris and Isis, Horus, has to avenge his father. And interestingly enough, that echoes throughout many other cultures. For instance, the plot of Hamlet, the king is the rightful king killed by his brother. Hamlet has to avenge his father. Even the Lion King, the plot follows the same ancient Egyptian Osiris and Set. And that shows that ancient Egypt knew. That number 72, henchmen, now that the earliest record we have of 72 henchmen of Set isn't really until Plutarch, much later, actually after Hipparchus, slightly after Hipparchus. But, as we said, Hipparchus didn't know the number 72 for precession. He only estimated 1 degree every 100 years, as far as we know. Plus, there's other evidence that the ancient Egyptians not only knew about precession, you can see that just from the myth. You know, the myth was long before Plutarch. We have evidence of the Osiris myth and Set all the way back in the ancient pyramid texts. But even before the pyramid texts, the Great Pyramid of Giza, look at the sides of the Great Pyramid, 432 royal cubits. You can measure it out, and even today you can see that the sides incorporate that precessional number. I'm going to show you a few more slides here. I'm just going to flash them up quickly for the Gilgamesh Series, extremely ancient texts. Some scholars believe 2600 BC, some think, well, maybe not quite that old, maybe 2000 BC, but 2000 BC as the lower limit of how ancient they are. They're at least from 2000 BC or earlier. And in that epic, there's a lot of precessional imagery, as I discuss in my book, in the myth itself, but also this idea of making a door 72 cubits high out of this cedar tree that Gilgamesh cuts down. I'm going to flash forward here to the Vedic literature of ancient India, these different ages. We just talked about the ages that are brought about by precession. Look at these yugas, which have precessional numbers of years associated with them. Also the Rig Veda, which was definitely pre-1100 BC. Precessional numbers. The Norse mythology of Valhalla. The Poetic Edda talks about how many warriors were in Valhalla. 540 doors in Valhalla, 8 could walk abreast. That multiplies out to a precessional number. A lot of people have talked about this prior to myself. I'm showing that the understanding of precessional numbers gives you the key to seeing that the ancient civilizations knew about it long before conventional history says they did. And also, it's global. There's lots of examples from the New World. I'm just going to show one here. Teotihuacan. The dimensions of Teotihuacan, you could argue about what unit they used. An American engineer named Hugh Harleston came up with a standard Teotihuacan unit. All kinds of precessional proportions using the standard Teotihuacan unit. But even if you don't accept his unit, those proportions are in there. Those multiples are there. So that's just one of the examples from the quote New World. There's many others. I catalog a lot of those in my book, some of which I haven't seen mentioned anywhere else. And that indicates a precise, those same precise numbers, did they just pop up coincidentally in isolation? That they came to the same precessional constant with that degree of accuracy? Or was there on some ancient cultural contact, and not just one-time accidental contact, but perhaps ongoing ancient contact? And in fact, there's lots of other evidence that suggests, in addition to the precessional numbers that are encoded here, there's lots of other evidence that suggests ongoing ancient contact across the oceans, which also indicates potential knowledge of the size and shape of the Earth. In order to cross the oceans deliberately and successfully, often those great mighty barriers of the ocean, it helps to understand the size and shape of the Earth. And there's actually ancient evidence, back to the Great Pyramid again. Look, the size, the perimeter of the base of the Great Pyramid relates to the circumference of the Earth. That's amazing. Now you might say, well, so does the size of my house. If you multiply it by some number, you'll get the so the circumference of the Earth at the equator, but look at what number you multiply the base of the Great Pyramid by to get a very accurate approximation of the circumference of our spherical Earth at the equator, which indicates that potentially these very earliest civilizations that we knew of were measuring accurately the equatorial circumference of our Earth. That completely upends the conventional timeline, as I said at the beginning. And so, in conclusion, you can see that the understanding of the precessional numbers is the key that enables you to see the evidence that these most ancient civilizations were extremely advanced and sophisticated. There's evidence that there was ancient global contact ongoing, that at some point in the ancient world there was crossing of the ocean barriers. It was probably the Romans probably put an end to it. There's some evidence that that's what happened. But this completely upends the notion of this linear progress of human history. There's other things that the ancients knew that was extremely sophisticated. In fact, things that even today we're still grasping towards, things about human consciousness, about deliberate out-of-body experiences. There's some evidence of that. Even hints of knowledge of plasma science or understanding of plasma, which is a fairly new field of scientific inquiry. Even some aspects of quantum physics. So understanding of precession enables you to see beyond this fabrication of linear progress and opens you up to seeing all kinds of other things that were apparently going on in these ancient civilizations. Thank you.